Well, I think we're about there. Welcome back, everyone. So for today's class, we're going to be possibly finishing chapter 14. We'll just see where we end up. If we don't finish it today, we'll move the due date back as necessary. So there's always a 1 week turnaround. But then after that, we're going to be getting into chapter 15. Chapter 15 is kind of titled in a weird way, Inference and Practice. I don't think that's the best working title for this actual section. I would probably call chapter 15 really more about confidence intervals, more about hypothesis testing. It's like an extension of chapter 14, really. So I did make a comment about chapter 13, or excuse me, chapter 15 right here. It's similar to chapter 13 in that I would say these two chapters are probably the more difficult ones in the course. Chapter 13 is a little bit weirder, worse, I'd say, because of the abstract nature of the central limit theorem. But chapter 15 is what I would consider hard because it has more technical kind of stuff we have to get used to. So they're both challenging in their own ways. And this would be a good one to pre-read, even if you're just skim a few ideas in there before we tackle it in full next class meeting. Any questions about those so far? Okay, probably the next important announcement is, of course, we're getting close to midterms week. But for this course, we don't have an official actual midterm exam. So there won't be any quiz, project, or special homework assignment or anything like that. Essentially, how midterms will work in our class is on Friday of this week here, I'll just take a look at your current course grade, and that's going to be your midterm grade. Just a reminder, you can always go up here and double check those. It's a good habit to really do that often, I'd say, for all of your classes. Make sure nothing's missing there, that kind of stuff. Well, that's our announcement so far. And also should mention, welcome back, folks. It feels like we have been away from this class for quite a while due to Valentine's Day. We took a day and the President's Day holiday. I hope that was a nice, restful day for everyone. But now we're getting back to example 6 on hypothesis testing. Any questions or comments, folks, to start us out? I guess I do have a question. We're not doing anything special for midterm week other than just reporting what your current grade is. But that also begets another question. When is the next exam, right? So if we keep scrolling, there it is on the very next week. We'll have it on Wednesday, March 6th. That means as we get closer to the weekend, I'll be providing more information here for the coverage and the sample review problems as well. And we're pretty much going to redo everything that we did coming up to exam 1. So in other words, if you have questions about exam 2 review material or anything along those lines, we can hold an informal review day on Monday of this week here. So it'll be pretty much the way we did before. It's all student directed. Hard to do the first time, but now that we have an idea of how it goes, it'll probably be a better review for the second one, I'd say. That's my full spiel of announcements. Any other questions, folks, before we go back to chapter 14? Okay, well, in chapter 14, here's where we left off. We had been practicing formulating the hypotheses, a null hypothesis and an alternative hypothesis, but that only gets us so far. We have to show how the actual test works. So here is the full procedure. Starts off by saying you need a simple random sample. So we'll have that of sample size n. It's going to come from a population where we're saying it's normally distributed, and we'll take that assumption off. Central limit theorem will help with that one. We'll have an unknown mean, which makes sense. That's the thing you're testing. So if you knew it, you would never test it. And this is the shadiest statement right here of all, and a known standard deviation sigma. We've been harping on that issue for quite a while. And chapter 17 is a time we'll finally correct this logical loophole, essentially. But for the moment, we're going to still run with this assumption. Think of chapter 14 as we're just practicing statistical inference. This turns out to be a good way to do it. For pedagogical reasons, we can get right into the nitty-gritty of things without going too far, too fast. So that's assumption we'll make. Next, it says, if you're going to do a hypothesis test, you need to determine what is your level of significance for that test. What is your criteria or benchmark for having enough evidence to reject the null hypothesis? That quantity is called the significance level alpha, and it plays a similar role as the confidence level. So in fact, if you do a two-tailed hypothesis test or a confidence interval, your analysis is really the same. And in that case, if you say pick a 90% confidence interval, the equivalent analysis as a hypothesis test would be a significance level of 0.10. We want our p-value, whatever that thing is going to be less than 0.10 if that's how we specified it. If we want more evidence before we reject the null hypothesis, we could drop it down to a 0.01. And that's like similar to having 99% confidence in your confidence interval. Again, your conclusions would always be the same. In a certain sense, the confidence interval is better because it doesn't just give you a conclusion, it also gives you an estimate for the parameter mu. On a hypothesis test, we're just going to either fail to reject the null hypothesis, but if we do reject it, we'll make one of these conclusions. Notice that's not necessarily an estimate. We're just going to say the parameter is either larger if it was a right tail test, smaller if it was a left tail test, or just not equal to the hypothesized value for a two tail test. But what people would do in practice then, after you do a hypothesis test, if you really reject the null hypothesis or don't reject it, people would still provide the confidence interval. Because if you're saying in a study that a parameter is less than mu naught, a follow-up question for you would be, okay, if it's less than that, what is it? What is your estimate of it? How far less are we expecting here? So I mention all that because statistics in a classroom setting is weird in a real sense. When we do a hypothesis test as a class type problem, we just end on a hypothesis test and make a conclusion. But in statistical practice, you do even more, give a confidence interval for a follow-up analysis. But still, we haven't described what do we do with the significance level once we set it? How do we determine if we're rejecting the null hypothesis? The first thing we need is the z-test statistic, or just simply called the test statistic sometimes. It's defined in this way, but let's blow that up a little bit and take a look at what's really going on here. When we formalize the null hypothesis, this is the value to be tested, or a hypothesized value. Now, if you look at the numerator here, we're measuring a difference. We're measuring the difference between the actual average of the data and the hypothesized value. But then it's divided by sigma over square root of n. We might wonder, where in the world does that come from? Let's put it up here. Because of the central limit theorem, the sample mean x bar will be distributed normally. The true mean would go here, but that's the unknown. We don't have any clue what to do with that. Standard deviation would go here, sigma over root n. And that's what's carried down right here, sigma divided by root n. So that means there is a particular unit to this z-test statistic. Let's maybe shove it to the left and say exactly what that unit is. This thing right here measures, let's say get this pen held right, there we go. The red dot moves around if I click on one of these buttons accidentally. But this thing is going to measure the distance or let's say instead of the distance, sorry for those working in pen today, it's going to measure the number of standard deviations. All right, STD for standard, DEV for deviations, that our data, the sample mean x bar, is away from mu naught, the hypothesized value coming from the null hypothesis. So now if the number of standard deviations here is large, say 2.5 deviations, 3 standard deviations, either positive or negative, we're probably going to get a very, very significant result because that would be unusual. But if this distance is small, if the z-test statistic comes out as a 0.3 or a 0.5, well, that just means the data is very close to your hypothesized mean. It's compatible with that statement now, and we're probably going to fail to reject the null hypothesis in that situation. So that's the role the test statistic plays. It's a pretty huge role here, so I guess it deserves a color. Let's go with green. There we go. We'll definitely need that if we're going to run through the hypothesis test. But then after you do that, here's what we do next. We'll use this symbol here, z, to refer to the standard normal distribution, meaning it's distributed with a true mean of 0. And that should have a true mean of 0 right here, because when you subtract this, you have standardized the value of z. It now has mean 0. Next, the standard deviation here is going to be a 1. And that ought to be the case because, once again, if you divide by the standard deviation of X bar right here, it's now standardized to have a deviation of 1 in this location. And that's why this is sometimes referred to as the standard normal distribution. We've changed all the values from up here the moment we subtracted mu naught and divide by sigma over root n. So much like with confidence intervals, we got all of our critical values z star from n0, 1, and same with p-values. All of our probabilities will be computed right exactly there. So our null hypothesis, our author always writes with direct equality. You can change that and do a different strategy like we mentioned before. I'll be copying this just because if you're reading out the text, that will be more familiar. But then here's where the interesting drama happens. There's 3 different kinds of tests you could write out as a hypothesis test. And that means there's 3 different formulas for the p-value. That's kind of tedious in a way. The good news is this one's the default. Something in the problem has to direct you to a right-tailed test or a left-tailed test. But we should describe all the formulas right here now just to see how it goes. First thing you want to do is just draw a generic normal curve. There it is. This is the distribution n0, 1. So the center this time is directly at 0 down below. Then, after you calculate your z-test statistic for measuring this number of standard deviations from the data, it could fall anywhere right here. But if it's a right-tailed test, our hope of hopes is it's really far to the right somewhere here, because that's going to make our p-value small. I'll just draw it generically in this location. So here's z. That area that we've highlighted there, that is now our p-value. And we can describe it pretty nicely by saying the p-value is going to be the probability that that z statistic right here, this random variable z, because it's a right-tailed test, we would say greater than lowercase z, where lowercase z is the original z-test statistic from here. So that's how it'd be calculated, but that's just the probability statement. What we'd be more interested in is the R syntax. It goes like this. There'll be p norm. We throw z in. What's kind of cool about RStudio is it makes a lot of assumptions. If I don't give it 0, 1 for parameter values, it's going to assume those are the intended parameter values. So I would just skip all that and immediately say lower.tail is false. So this statement right here gives us the p-value if you're doing a right-tailed test. If you're doing a left-tailed test, it's kind of nice. All you do is you just take that statement off, and that's the right formula for your p-value. Let's draw a picture out just because it would seem wrong not to. Let's put it right here. So another fast normal curve. Okay, now that we've got the curve, the way I drew z right here, this is what it would look like if we failed to reject the null hypothesis. There's quite a lot of area here, so a probability would be around 0.25 potentially. We want probabilities less than significance level alpha, so we're looking for things less than 0.10 at worst. We're probably more wanting things to be less than 0.05 or even smaller if we can. So this one wouldn't be significant. We would fail to reject the null hypothesis. On this one, this is what it would possibly look like if we did reject the null hypothesis. And conclusion, the alternative. This time, there's very little area right here, so our p-value is small, and that says this number of standard deviations must have been large. The sample data x bar must have been incompatible with the statement mu naught from the null hypothesis, and so that's why we would reject it in this picture right here. This would be our conclusion, and we would just have to read this out, saying what mu is and those kinds of things. So in this case, the p-value, I'm not sure how to draw that arrow. There we go. Let's just snake it around. Let's skip directly to the R syntax. This one is just going to be simply p norm z. And again, that's all you have to give it. It's going to assume you're working in the standard normal distribution, if that's all you give. We want area to the left, so we didn't even have to say anything about lower dot tail. So the left tail test is kind of nice in that sense. It's a really fast statement. We've practiced so much with the normal distribution, this is really nothing too special at this stage. Now, it's kind of sad then that the two-tailed test, the one that's probably the most important, the default test, this one's a little bit sketchier to describe, but let's describe it the best we can. It says verbally, we need to take twice the area under the z-curve to the right of the absolute value of z. That's what our author does, but let's write out the formula or the sketch first. So here's another N01, probably poorly driven. It really shouldn't come up right there, but we're not trying to draw them perfectly. I'll put a 0 here. And now this is the challenge with describing the formula for the two-tailed test. When you're doing a two-tailed test, there's really no expectation on your test statistic z. It could either be positive, way out here, negative out here, and even if it's really far to the left or really far to the right, that's not the whole picture. A two-tailed test is going to grab areas from both tails of the normal curve. So if your z-test statistic is right here, you need this area, but then you have to jump across 0 symmetrically, put in negative z, because you need this area too. So that's the trouble with describing this formula. There is 2 locations where we're accumulating probabilities, but the good news is this is symmetric across 0. In fact, the symmetry is perfect. So if you just doubled this area, that is the right p-value. You would give area here and here. So that's why it says twice the area under the z-curve to the right of, it has to say this, absolute value of z, because I don't know if z is positive, it belongs here, or if z is negative and it belongs right here. So that's another issue with the trouble, but we can get around all of this by saying, in this case, let's use 2 arrows just to communicate, we're getting area for both of this statement. The p-value is going to be equal to, and this is kind of silly, but this is the easiest thing to miss. It's twice the area. And so it's actually easy to miss the fact that you're going to put times 2 right there to actually double that area. I've forgotten quite a few times myself. That's always kind of weird. But then once you get across that difficulty, it'll be 2 times p norm. Our author likes to take the area to the right of the absolute value of z. Now, there's a lot of ways to do this. You could take negative absolute value z to force in this area. But if we're doing it exactly the way the author describes, it would go like this. ABS z, now you've taken the absolute value of z in RStudio and put in lower dot tail equals false. So that's our author's way of doing it. I don't particularly like it because of this right here. It's a kind of a long statement, but it works just fine. If you want to make your syntax a little bit smaller, this also works just as well. It's right down here. Or you can use the formula, p-value equals, let's put this emphasis in once more because it's super easy to miss. So twice p-norm. If you want to make real sure you're getting this area right here, you have to in fact go negative ABSZ. So if z was a negative value, and you threw a negative in front, you're not actually right here anymore. You'd be on the right tail. So if you take the absolute value of z, now we've forced it to be positive, the negative is negating it. Now we're exclusively right here no matter what. Mathematically, that's just your location. And that means that's the whole syntax. We're getting area to the left, and that would do the job. So either way you'd like to do it, you'll get the same result. I usually do it this way only because it's just faster to type out. Well, any questions, folks, with getting through those p-values descriptions? Okay, so pretty much the major formulas that we'd have to take a look at to get through this. We first decide which test we're really writing out, and this does the job. I'll highlight both of them, not to give anyone any specific preference. So either formula would work on that case. Then let's suppose you got the p-value. What you want to do immediately is whatever this p-value comes out as, we compare it against the significance level alpha right away. And here's why we're doing that. Recall there's only 2 conclusions we can give. We'll keep on emphasizing that because it's also easy to miss. But it goes like this next. If your p-value is small, that means we have significant statistical evidence that the null hypothesis is not true. In other words, we have great evidence that the alternative hypothesis is the actual truth of the population. But if the p-value is large, notice the greater than or equal to right here. We want our p-value strictly less than alpha, whatever alpha is. If it's a large p-value, this is what happens. We will write out a conclusion that says either the study failed to find significant statistical evidence that the alternative hypothesis is true, or you can write this out in other kind of ways. But what we can never say is we found evidence that the null hypothesis is true. The reason we can't say that is we're following the logic in a court of law pretty much exactly when we do hypothesis testing. And just as a reminder, in a court of law, it's assumed immediately that you're not guilty. Then people march out evidence. P-values are our evidence in statistics. And if there's enough evidence against the statement that you're innocent, that's the null hypothesis, we reject it. There's the rejection right there. And we conclude the person is actually guilty. That's the alternative hypothesis. But if we didn't find enough evidence to say the person is guilty of something, well, the person gets left off. But in a court of law, that is not saying we proved innocence at all, not even close. We might still highly suspect the person is guilty, but we couldn't produce the evidence to actually prove it. We're in the same scenario. If our p-value is large, we'll never express that we found evidence that the null is true. We will say we just didn't find the evidence that the alternative is true instead. Again, that's really easy to miss with hypothesis testing, so we'll harp on it a few more times as we go through the notes. But finally, this is pretty much the full description. Really, the major formulas we need are the right ones for p-values and the formula for the test statistic right here. Any questions at all, folks, before we run down a full problem using these ideas? Okay, well, this problem is kind of nasty in a way, but the reason I brought this one out is this is sometimes what statistics looks like in real life. There's a lot of fluff here. Our job is to find the actual right information we need amongst all this noise. But first, Olivia asks, so we can never say the null is true. That's absolutely right, Olivia. We have to say, if it's a large p-value, simply that the study failed to find evidence that the alternative hypothesis is true, rather than saying that the null is true. Does that make sense so far with that question? You bet. I did want to expand a little bit on that. That's actually a really good question, Olivia. Let me put a bit of notes right here. Sometimes people don't necessarily give this exact statement right here, that the study failed to find significant evidence that the alternative is true. Other times people might give this kind of conclusion. I would put here a little bit of emphasis that this is kind of a sketchy one because people have to know exactly what you mean when you give this conclusion. It's super easy to misconstrue. You might say, for p-value, bigger than or equal to the significance level alpha, one conclusion might be that the data is consistent with H naught. That conclusion is not entirely wrong, but again, it's extremely sketchy because people can read this out and say, we found evidence that the null hypothesis is true. We did not. It's just that our data that we pulled in happened to be consistent with it. That's not a proof that the null hypothesis is true at all, unfortunately. But other questions about that, those ideas so far? Okay, I would say avoid this kind of conclusion, but it is correct. Use it with caution, maybe at worst, is what I would advise. But the more you take statistics, the more work you do with it, you'll get a better feel for when the statement is appropriate and when it probably should be avoided. Well, let's take a look next. We're going to provide a complete analysis on this problem. And sometimes we'll pick our confidence level or significance level. Other times a problem supplies it. This is a good one to identify right here. It says use a significance level of 0.05. So what they're telling us right here with that statement is our benchmark for evidence to conclude an alternative is true is p-value has to be less than 0.05. So that's our benchmark. Scroll down here. First thing we need to do for a statistical problem like this is start breaking it down, finding the actual right statistical information to get started with. It begins by saying the Board of Health of our particular state was called to investigate claims that raw pollutants were being released into a river flowing past a small residential community. Now, this is a made-up problem, but you can imagine this would be a very, very important statistical problem if this was something, say, happening around Idaho Falls, for example. Goes on to say, by applying financial pressure, the state was able to get the violating company to make major concessions towards the installation of a new water purification system. They go on then to say, in the interim, that's a weird word. Think of that as saying, meanwhile, different production systems were to be initiated to help reduce the pollution level of water entering the river. That's fantastic. All that's important. It's context we need. But there's no actual statistical information right there that I can record that's going to help us move through the hypothesis test. Still, it's worth reading, but let's see if we can find anything in the next statement. It says next, to monitor the effect of the interim system, the system they're using while they're trying to get around their legal issues, a random sample of 50 water specimens measuring the dissolved oxygen count in the water was taken throughout the month at a location downstream from the plant. Now, that's starting to look a little bit better because if they say a random sample of 50, first, that's helping with conditions. We know at least it's random some way, somehow. And writing this down is actually a really huge help. It's going to help us track through the formulas if we record each of the elements needed in our own notation. So we found a sample size of 50 from here. And let's talk about this right here. The reason they're interested in oxygen count of the water is if you dump raw pollutants in water, that count will go down. At least that's their expectation. So they're starting to track that carefully. If the interim system is actually working and they're not dumping pollutants, then we expect our dissolved oxygen count in the water to not be so low. It should go back to normal levels. So here's what they say next. The sample mean of 5.0 parts per million was obtained. That's good information. If you see this right here, then because it said sample mean, they gave us X bar. So now we have X bar equals 5.0. It's always good to put it in the unit. If you have the extra time and it's not a long unit, it helps us with the context as we go through the problem. It says now, assume the population standard deviation of dissolved oxygen content in water at this location is 0.70 parts per million. So to me, that's pretty sketchy information. If we were doing this as a consulting company, we would just have to trust the experts because what they told us is sigma is 0.70 parts per million. We might wonder, why didn't we just use the sample data to calculate S? And historically, that's what people actually did. They took S, the sample standard deviation, and they just pretended that's what sigma was actually equal to. Did they get in trouble? Probably not if their sample size is at 50. Central limit theorem is starting to work really well. Your estimate of sigma through S, the sample standard deviation, gets better. But if your sample size gets low, say 10, or even a sample size around 5, those happen in real statistical studies, this breaks down massively. You can't just put the statistic here. There will be huge problems. So we'll see in chapter 17 again how to correct all of that. Well, down below it says, is there evidence that the mean dissolved oxygen count of the water is less than 5.2, which was the mean reading of this location over the previous year? Probably they were dumping raw pollutants in the previous year. This value right here is also important. Let's highlight this one in yellow. In fact, let's highlight the whole question in yellow. Oftentimes, when you see a question like this in a hypothesis test type problem, that question mark is almost a dead giveaway. This is a statement for the alternative hypothesis itself. We're going to convey this as an alternative hypothesis. And that means this 5.2 value right here, that's the value to be tested. So we have mu naught, not right here, or sub-zero, meaning we're going to plug that into the null hypothesis. This is the hypothesized value, is 5.2 parts per million. So already it looks like there's a problem, right? Sample mean clocked in less than the value last year, but that's not the whole story in statistics. You also have to bring in the variability, sigma. So we'll see what happens in this problem if we find that evidence or not. We'll test it at a level of 0.05 significance. But even that statement right there, it's a good idea to take this and just convey it using our notation. Alpha is 0.05. The importance of that is if you write it in our own notation, then suddenly this table makes a little bit more sense. Again, this is the struggle with statistics. People who write out these problems are not going to necessarily say X bar, so we shouldn't expect it either. Our goal is to extract it from the problem and start recording these values so we can run through the problem in an efficient way. So probably the best strategy is read the whole problem, then read it again. Try to indicate each one of these values to your best of your ability. Maybe read it a third time to make sure everything is right. Then when you run through the problem, in particular, after you give a conclusion, good idea to read it again, even still. Maybe you've read it 4 or 5 times, but sometimes with these kinds of problems, it takes that much effort to just make sure every subtlety and issue in here has been properly looked at and conveyed in our conclusion. Ooh, so that's pretty much our start of the problem. We found 5 different values that are going to help us. And because it's a complete analysis, we're really doing a 4-part problem in a certain sense. That goes like this. First, we want to state what is the practical question that requires statistical inference. There's a lot of things you can say here, but you might say, just very briefly, is the interim system effective in reducing pollution from raw sewage? So we didn't say anything too interesting along the lines of what is the parameter or anything like that, but this seems to be the major question that caused a whole study to be executed with a sample size of 50. We just want to know, are they still dumping raw pollution into that river? So something like this is always a completely fine response. If you took this whole question mark, or this whole statement here with a question mark and place it there, that's appropriate as well. All you're really doing on this portion of the complete analysis is indicating to me that you know exactly what the problem is about. And there's lots of ways to do that. Usually I only assign about 1 point to this. It's usually not a major part of the problem. But I've noticed that when we emphasize this a little bit more, everyone's conclusions are a little bit better. So it must help in some way. Well, here's where we're going to start moving through the hypothesis test in earnest. It says here for the planning phase, clearly define the unknown parameter using the context. Pretty much what we were doing from day 1 of the class is this right here. When it says the unknown parameter, even if sigma was unknown, what we're really talking about is mu. We're not talking about X bar. We're not talking about mu naught either. We're talking about this thing. That's the thing we're doing a whole hypothesis test on. And so if it says unknown parameter, it's almost definitely referring to this right here. We just have to say what it means in this particular context. Now, because we used mu, we're dealing with quantitative data as we expect. And you could start off by saying the true mean, or you could say the population mean, or you could say just simply the mean of all whatever the population is. I like using this word here, true mean, because it emphasizes the fact that we don't even know what mu is, but there's some value out there that we're trying to talk about. We're not talking about this one. This is the value from last year. And we're not talking about these data. This is just estimating the unknown right here. So this will be the true mean of something. Any volunteers for finishing out this statement? It's definitely tricky, right? But there's kind of a strategy for this. One way you can decide what it is, well, if you said mean because you used mu for the parameter, go back to this one. X bar was estimating mu, had units of parts per million. That actually helps quite a bit. And it came from a random sample of 50 water specimens measuring dissolved oxygen count in the water. So that's our hint on this one. This is the true mean of the dissolved oxygen content in the river. And I'd say this is pretty good, but it's still not quite there. There's just one extra comment we have to make because there's really two populations. This was the dissolved oxygen content last year, where presumably there wasn't raw sewage being dumped in. Then they did dump in raw sewage, but then they changed it. Their process, there's some interim system that's being ran, and we want to know what is the mean during this interim system. So we'll put down here, this is the true mean of dissolved oxygen content in the river, while the interim, it's a weird word, system is in place. And I really don't think I planned on how much space this takes. Let's get a little bit extra in there. And we've got it, folks. That's our value for the parameter. Any questions or comments about coming up with this parameter mu? Okay, I often find that this is a pretty tricky step in this kind of analysis. So if you're doing this as a homework question, you can always write this right by me. You can just send me an email. Hey, Mike, is this about what mu should be in this problem? And I'm always very happy to help out with that kind of stuff because, again, it's tricky. We'll get very good at it once we get through the course. But for now, let's now go to the next portion. We want to define the unknown parameter. Really, we're just describing what it would be. Next, we're going to state the null and alternative hypothesis in terms of that parameter, as well as the hypothesized value right here. So it'll go like this. H naught. This is a statement that nothing's changed, and it would be written this way. Mu is equal to, we take the value of mu naught, 5.2 parts per million, and that's our null hypothesis. Next, we're going to test this against the alternative hypothesis, HA. We put mu here as well. We use the value to be tested again, 5.2, with a little bit of space between. But now we have to decide what goes in the middle. In other words, is this a left tail test? That would mean you're putting a less than. Is it a right tail test for a greater than? Or is it a two tail test for not equals? If you're not sure, this is the best one to go for. Maybe you might lose a point here or there, but there's always partial credit. If you go for this one, you're pretty much in great shape. But if the problem directs us to one or the other, we have to go for the other tests to get full credit on this kind of problem. So I'll leave it up to the class and let's see what kind of test this one should be. I agree with the less than. It said here, is there evidence that the mean dissolved oxygen count of the water is less than 5.2? Again, that's pretty much your alternative hypothesis, so good call. From right here, we should just match up a less than in that location. Sometimes it's kind of tricky how they convey this information, but again, if you missed it, you might lose maybe 1 or 2 points on the whole problem. Nothing too major. But we've got a left tail test. And sometimes what's a pretty decent idea with this is, I'm not super picky. If you've got your null hypothesis, that's great. Your alternative hypothesis has to be written in. But it's not a bad idea to also state the level of significance as well when you state your hypotheses, because we need to come back to that. It's just a good reminder. And maybe one last comment. Our author always puts equality right here. And this is very disconcerting for any student, and I'm sure there's plenty of us who are taking the biometry lab. Because in biometry, it is correct to say the null hypothesis and alternative hypothesis are completely contradictory statements. If you're making a contradiction here, negating this statement, a true negation actually looks like this. You flip the sign from less than to greater than, and include the possibility of equality. That's just as good as the other one that we put in. It includes equality as well. Our author goes for this statement every single time, and there's sometimes good reasons for that. When we go to get the p-value, we're actually using that value 5.2, no matter what tester you're actually using. So that's one of the reasons our author always goes this way, and we'll see a second reason in the next chapter. But just as a reminder, if you're doing it the biometry way, that's completely fine as well. Everyone will understand your meaning if you go greater than or equals here. Well, any questions so far, folks, to this stage? Okay, this portion of the problem is really nothing major. We can't do much checking here. What we're looking for is any statement about normal randomness when they selected the sample, they set it up here. So if we were to write down something, we could say the sample is random. We're not sure exactly what the sampling design is, but in this class, we won't worry too much about that. You'd have to have a real problem and you'd have to read the entire methods in that journal posting for it to know if it was a simple random sample or not. We're not trying to go that in depth with the analysis. We're just trying to find if there was at least something that tells us randomization might have happened. So we know it was random. Other issues here is we need a normal distribution. In our assumptions for this particular test, that was one thing that was required. And that's something we can't even check here, if that's even a reasonable assumption, because this was all summarized data. There's no actual raw data that was provided to us. So we can say next, because of that limitation, the conditions are met, provided, scroll a little bit here. So the conditions are met, provided that the sample size of 50 is effective enough to overcome skew in the population. Again, if we had the actual real data, we would throw that into a histogram. And with 50 observations, we'll get some pretty good indication if the underlying population even was normally distributed, just based on how skewed the sample data might have been. But in these kinds of problems, we can't really say too much here. And so when we do the grading for the condition checking here, I'm not looking for too much. We're really going to delve into conditions a lot more once we're in chapter 17 with our more honest methods that don't use a value for sigma right here. So think of this as just a warm-up. But any questions, folks, with what we wrote down there? Okay. Part 2 of the solve phase says carry out the necessary computations. And it always goes in kind of 2 phases if you're doing a hypothesis test. Phase 1, what you need is the test statistic. So let's write that in. This portion right here has the potential to be an exam 2 question. And to get good credit on this one, I would probably start off like this. Z is going to be equal to X bar minus mu naught divided by sigma, which is also divided by the square root of the sample size n. Now at this stage, we're just going to look up the values that we posted above and start plugging them in right here. But in an exam situation, if you write down this much, I would give partial credit just for that. You're conveying that you know how the formula should go. Any mistakes here, you could lose some points, but not anything too major. So on our next step, we'll say that this is equal to, first we need to find our X bar. It is up here above at 5. We'll subtract from that the value of mu naught. It was right here in the statement for the alternative hypothesis at 5.2. On our next step, we need to look up sigma. It was given to be 0.70. And finally, that's all divided by the square root of the sample size, which was indicated to be 50 in this problem. So this right here would be considered partial credit. And on a real exam, you're always going to be massively encouraged and reminded, definitely put that on paper. Because if you plug all this into the calculator without actually putting it on paper, I could lose all basis for partial credit if just the simplest calculator mistake was made. And if you do make a simple calculator mistake, but this is posted, you get essentially almost all the credit. I might take off a half a point because I understand it's easy to miss key stuff when you're doing stuff in an exam situation. But it's really not too bad to calculate. Let's grab our studio. We'll just use it as a calculator. So let's type it into the console. For numerator, we need 5 minus 5.2. For the denominator, go 0.70. Division, and for that symbol, SQRT is what you need to call the square root function. And that's finally our test statistic. It's negative 2.0203. And I would say for the test statistic here, 4 decimal places is pretty standard for rounding if you decide to round. Let's put here just as a note. Round to 4 decimal places. If you do decide to round, again, you don't have to round. And in fact, I'd probably encourage you not to round in this kind of problem. Instead, in RStudio, I'm just going to take this number, which has more precision than it looks like, and feed that into the formula for the p-value. So really, there's just rounding on paper to report the value, but we're going to use the more exact value right here. Well, any questions, folks, on the test statistic portion? Okay, next thing we need is the p-value. Let's just leave it blank here. And here's a great way to think about the p-value. You could say, go to the test. The alternative hypothesis right here is a left tail test. So the picture should look like this. Next, we found z is negative 2.0203. That would be about here. It means all this area is what we need to calculate the p-value. This won't be on exam. I'll have to calculate the p-value for you, but your job will be to give the conclusion on the next step. Back to RStudio, it's just going to be a matter of, let's see here. Write in p norm. We want the area to the left of this value. And over here, let me try this again. I was going to try to use this exact value right here, but that's a little bit trickier, this calculator. You would hit the up arrow to get that and go p norm on this whole thing. But honestly, that looks kind of awkward. Maybe a better way to go is, let's just use the syntax field right here. I think that's going to look nicer on the notes. So z would get 5 minus 5.2 divided by 0.70 divided by the square root of 50. There we go. So now it's printed in. Then just go p norm z. Here, that's going to accumulate area to the left. I think that's kind of a nicer way to see it. Oh, see it and calculate it on this. Oh, geez, I hit Control Z too many times, I think. Sorry, I'm struggling with the technology here. Let me fix this real quick. Okay, there we go. And we get the p-value we're expecting. This one, honestly, 4 decimal places is pretty standard. But for significance level alpha is to 2 decimal places, maybe rounding to 3 places just makes sense in this kind of problem. I'll report all 4 values. The p-value came out to a 0.0217. Well, we did it, folks. That's our p-value in the problem. Let me take this. I've been forgetting to put the syntax in these problems, so let me paste it in right here. But in a way that's kind of nice. There's not a whole lot of RStudio to get through the hypothesis test on this one. There's just some basic calculator work, a quick p-norm function, And there's our p-value. Now, before you go to the conclusion, even though we really finished everything on the solving phase, it's sometimes a really good idea to now look towards the top of the problem, right where you wrote out all this stuff right here. Let's just put down a temporary screenshot. The moment you see that p-value, what you really want to do is compare it against the significance level alpha pretty much immediately. Let's put down here, it's a 0.05. So this is less than a 0.05, which is equal to alpha. So now we have something less than. Let's remind ourselves, does that mean we reject the null hypothesis, or are we failing to reject the null? Any volunteers for what the right decision should be for right here? Exactly. Again, good call, Olivia. We're going to be rejecting the null. So that's what we really want in a statistical study. Oftentimes, the alternative hypothesis, that's your research question you're very, very interested in. So your hope of hopes is a small p-value. But notice one thing you can never do in a hypothesis test is if this was a p-value up here at a 0.01, because the study was just planned to do that, and then you got your data and it came out as a 0.02, we cannot change the significance level alpha at all. In fact, all of this stuff is thought about, even the parameter is defined well in advance of collecting any data at all. If we change anything after we see the data just to try to force an outcome, at that point, we're doing something massively unethical in statistics. We're just essentially lying at that stage. Let me put that back to a 0.05. So once that's nailed down and we start collecting data, this is pretty much the letter of the law for hypothesis testing. You have to be less than that value and no changing there. But next statement you might make is, we will reject H naught. So coming down below, we're about ready for a conclusion. Any questions first, folks, with where we're at so far? Okay, since we said we're rejecting the null hypothesis, visually, this is what it means. That's completely off the table. We're just going to chuck it away. Our whole practical conclusion, being mentioned right here, even the context, is right through here. All we now have to do is just write it out. Now, one thing that's a little bit weird, and I guess it's just a tradition for this kind of work, is we don't always report the significance level alpha, giving this kind of conclusion. But for confidence intervals, that's a massive requirement. You should say how confident you are. To me, that's a little bit weird. So if that bothers you as well, here's a way you could write the problem. We found evidence that this is true. So I'm going to start by saying we have significant statistical evidence. Now, here's the optional part. You don't have to put this, but sometimes it helps. At the 5% significance level, that, and we're essentially going to say this is true. But there's a good reason why sometimes we don't say this portion right here in the conclusion. What we're trying to give is a practical conclusion using as minimum terminology as possible, and makes a lot more sense to say confidence. That's just the success rate of the method. But the significance level alpha, that is a lot harder to describe in practical terms. That's more technical information. That's part of the reason it might not always be there in a practical conclusion for hypothesis testing. But that's just an opinion. So if you feel like you ought to put it in, just like we always report confidence, I'd say go for it. Throw it in there. That is probably a good idea. So we have significant statistical evidence that, and this is kind of nice. It's kind of how we gave a practical conclusion for probability with normal distributions. We just go over here and read everything out. We can't use the symbol mu. We have to say what it was. So this is the redundant part of the problem. We have significant statistical evidence that the true dissolved oxygen content in the river while the interim system is in place. This is a little bit faster if you're typing it out, but it really wears on the hand writing it 2 times. But that we just say is less than. So pretty much we're writing this out verbatim. And it's less than the figure of 5.2 parts per million. And we did it, folks. That's the whole conclusion for the hypothesis test. Hypothesis testing is weird. I have to admit that up front. It's got a lot of extra nuances as compared to a conference interval procedure. But we'll see these quite a lot in chapter 17, 18, 19, and so on. So if it seems really foggy right now, I think that's kind of normal for this kind of work, unfortunately, and it gets better at the time. The good news is when we formulate these hypotheses, they always kind of just look like this. There's going to be some changes, but that's when we're deep into the course, nearly done with the semester. Well, any other questions or comments so far, folks, with the conclusions so far? Okay, I want to be upfront. I'm not super picky when I grade these. If I saw this conclusion, you're really completing the objective of statistical methods. You gave it the right kind of conclusion, but in a certain sense, this is an unsatisfying conclusion. Let's go up to what we said at the very beginning and get rid of all this stuff while we're at it. The actual question that we were trying to answer is this: is the interim system effective in reducing pollution from raw sewage? We answered it indirectly, but we didn't give a direct answer just yet. We ended right here. It's like being kind of a politician. We didn't put a direct answer to the statement. But if we go back to the top, here's what they were trying to say. At 5.2, this is when no raw pollution is being dumped. But then once you start dumping raw pollution to the river, the oxygen content goes down. We found that that's actually significant. So we get to say, we have found evidence that the interim system is not effective. They're probably still dumping raw sewage, or maybe the amount they dumped still has ramifications for the water system. So down below, we are going to say the bold statement that we have evidence that the interim systems are not effective. And that's where statistics and hypothesis testing can get a little bit technical in chapter 15, because we have to wonder, if you did consulting on this problem right here for the city or the state or whoever it might have been, are you going to get in trouble? In other words, did we do the statistics correctly, or do we make a particular kind of error in the statistics? If everything was done completely fine, then even if our conclusion is wrong, we're still going to be okay. But we might draw the ire of this company if they in fact are not polluting. And just by randomness alone, we've got a sample size of 50 where the content was low. Maybe the sampling design was messed up, or by just the randomness of hypothesis or pulling random data, the null hypothesis could have been true, and that could have been false. We might have made an error referred to as a type 1 error. And this is where hypothesis testing becomes pretty high stakes. Whenever we decide on a null and alternative and we pick alpha, we're trying to balance the kind of errors we might make when we make our conclusions. If we don't do that correctly, there could be huge and dire consequences depending on just how impactful this kind of problem is. Is the polluting company wealthy enough to come after you with an army of lawyers or something like that? Is the kind of real concerns people would have doing statistical consulting work like this. So that's the purpose of chapter 15. We want to know, what does it look like to make a mistake, how to control those mistakes, and if we are trying to avoid getting sued, or if we are starting up a statistical consulting company, we would also want to say, what is the power of this test? And that's an impressive word, right? The power of a hypothesis test. That's the objective of chapter 15. we want to ascribe a probability of correctly rejecting the null when a specific alternative is actually true. And if we did that planning phase, there's essentially no way we could ever be sued for making a wrong conclusion because we did all of our due diligence. So that's kind of the preview of what's happening next in chapter 15. But any questions, folks, with any of those statements or the conclusions down below? Okay, well, I have a couple extra problems down below. For example, 6. These are kind of just concept questions. They're questions that could turn up again in an exam setting, and they're also going to be pretty helpful to support us through the homework as well. Let's get these on a new page. First concept question is an important one, right? We've said quite a few times, we can never actually accept the null as being true when we give a conclusion of hypothesis testing. Any volunteers for the reasoning of why we could never do that? Anyone over Zoom happen to know what would be the reason we can never make this our conclusion, that the null hypothesis was accepted as true? It's a pretty tough question, right? And in statistics, there's actually a lot of contention between practicing statisticians. The contention is a lot of times in statistics, that is what you want to try to show as true, but you cannot do it in a hypothesis testing. It is a massive frustration in the sciences. The whole reason is, I'd say this is the tersest reason you could give as, say, an exam question. We cannot accept H naught as true because the process of finding the p-value starts with, and this is the major takeaway, let's give this a good color. It always started with assuming H naught is true from the very beginning. And then we just looked at how compatible this statement is, whatever it is, with the actual data we collected. We're just making a measurement through a p-value to see how compatible it is. But none of that work actually establishes H naught as true or false. We're just saying if it was true, what are the probability of getting the data that we actually collected? So that's the major takeaway on this concept question right here. Any questions about it so far, folks? Okay, the next one is worse. To me, this is a very confusing concept question to get through. Because once you gather, say, your p-value, 0.0217, let's suppose that it was greater than a 0.01. Maybe alpha was just much smaller here. That is not the probability of the null hypothesis being true, unfortunately. That's really kind of confusing. So if this was a 0.93, there's not a 93% chance that the null is true. Not at all. It's a different kind of probability. And if we can specify exactly what this probability is, well, that will definitely help us. Now, just a word of warning on this. We are not giving a practical interpretation. This is completely impractical. This is purely technical on how we got the probability. Let's make that a mention here. This is not a practical interpretation. Whenever we say practical interpretation in this course, and we've been using this verbiage exclusively to mean we're giving a conclusion that everyone could understand, even if you've never taken statistics at all. That's not what we're going to say here. It says for part B, the p-value is not the probability that the null hypothesis is true. What is the correct interpretation of that p-value? Now, this one's kind of tough, but any volunteers for what it could be? Again, these are some of the nastiest concept questions. So if you're not sure, then you're in the right class. If you knew exactly what this was, probably you should be in a more advanced statistics class. But here's how you can possibly write it out. The moment you've got a p-value, you can say the p-value equals the probability of obtaining data as extreme as the data in this study. When we say as extreme as the data in this study, we mean X bar was at 5.0, but the hypothesized value, prior year's value, was 5.2. That's already pretty extreme. It's far away in terms of the standard deviations in the problem from the last year's value. This is not the full statement, though. We say as extreme as the data in this study, or more extreme. What we mean by that, we're also involving the probability of X bar being less than 5.0. We need to see what would happen for even more extreme data, assuming the statement H naught, and in this problem, it was a statement that mu equals 5.2 is actually true. So that's our full statement of what the p-value is really measuring. So we want to know what is the chance of getting data this far away from your hypothesized value, or even more far away, when that would actually be the truth of the population. We don't suspect it is, it's just the value to be tested. But the further this gets away, the smaller your p-value becomes, and that's what it's trying to measure. How extreme your data really is, or how compatible it is with that statement there. Well, any questions, folks, about the statement below? Okay, I'd say these are pretty tricky concept questions. I don't think I would throw this one on an exam setting, but it's good to be familiar with because these are kinds of concept questions that could come up in a homework type problem. So if you see weird questions on the homework, this is a good set of notes to scroll through. Look for the problems after the hypothesis test, or look for the problems right here. There's concept questions about confidence intervals, and you could look right here after we did the confidence interval procedure for guidance on how those ought to go for the actual homework problems. Well, we ran into the very end of the notes, it looks like, folks. Any questions at all with what we've done so far? Okay, let's save these up, and I want to give you just a preview of what we're getting into next section. In the next section, again, inference in practice is kind of a weird title, though better working title is probably more plotting a study. We're going to start by saying, what is the right sample size in order to hit a targeted margin of error? That's if we're doing confidence intervals. But then next, most of the work is going to be right here. We need to break down this information, talk about the significance level alpha again, effect size, and our major objective of these notes is actually power of a hypothesis test. Whenever we do planning a study, if you're trying to land a really sweet government grant, getting all that funding, you have to do your due diligence and say, what is going to be the power of this test of correctly rejecting the null hypothesis when some specific alternative hypothesis is actually true? This takes a little bit of work to get through, but chapter 15 is going to focus a lot on type 1 error, type 2 error. To me, that's the technical part of all of this. It's pretty tricky to break down, so any pre-reading you do on chapter 15 will help tremendously on Monday's class. Well, I think I've definitely had a gas so far and out of things to mention. Any other questions or comments, folks, so far? Okay, well, this will be a good stopping point, so we're not breaking these notes in half. I don't think we can get too far in 5 minutes. So have a great weekend, folks. And at this point in the course, I don't think we have any weird interruptions. We'll probably much be working through until spring break, and then after that, all the way to finals week. Well, have a great night, and I'll see you all next week. Thanks, folks.